Hey folks, this is Major Jones here to talk to you about something called control hazards. So this is another problem I have to deal with in my pipeline now. We're going to describe what those are and learn how to identify them. And then just like the last lesson on data hazards, we're going to learn how we might resolve those control hazards with a method called stalling, which also has a software and a hardware implementation, and what the effect on performance might that be. All right. So let's take a look at control hazard. Control hazards result or occur, anytime I might have a branch instruction. So you can see here I've got another sort of little hypothetical piece of code that might run on my LC3 pipeline, and the pipeline is set up so that every time an instruction moves into the next stage, the program counter just increments. So you can see here these first four instructions, branch, add, store, that they sort of fill the pipeline all the way when I get to here in this execute phase. And if I don't take my branch, or if I'm not branching, then the next instruction is add, and the one after that's add, and so this is fine. But if I do take my branch in this code, I'm not executing the add instruction next. I should be executing a load instruction. And so I've got a control hazard because I got to deal with now that there are instructions in my pipeline that should not be executed because I'm taking my branch. And so there are a couple ways we can do this. Number one, kind of like the data hazards, I can insert no ops every time I have a branch in my code. And so if there's a branch here, I know that I'm not going to fully know whether or not I take my branch until this execute phase. So what I might have to do is just insert no operations in these three phases, just completely sort of stall the processor until I know for sure where I'm going to branch. And then by the time the branch executes, whatever instruction is fetched next will be the correct one. Like the data hazards, the downside to this is that it exposes these implementation details to the programmer. And so now all of a sudden, if my microarchitecture changes, if I add or remove a stage in my pipeline, then potentially programs that are written for my computer have to change, which is not the best strategy. We'll look at. So this is the hardware one. So again, just like data hazards, I can also do this thing in hardware. So I can alleviate the programmer from having to know about these no-ops. I can do that in hardware. And so I can add something called a branch unit, sort of like my data lock unit, which detects if there is a branch in my pipeline. And in this simple solution where I'm just inserting no operations to let the branch resolve before I fetch another instruction, then the logic's pretty simple. If the opcode in the fetch stage is one of these branch instructions, right? Branch, jump, JSR, then I'm just going to stall. So sort of like in the data hazards lesson, right? Stall meant that the program counter and the instruction register don't change. So coming back to my control hazards, what that means is I'll keep whatever. So in this example here, the add instruction would sort of stall in the program counter. It would wait there until the branch instruction made its way to the execute phase. And I missed that. The other part of this conditional is I'm going to stall this because I want to basically kind of insert this little no operation when the branch instruction gets to the read register phase and the evaluate address phase, then I insert bubbles behind it. So sort of like the data hazards, right? If I detect this branch instruction, then I'm going to let it move forward, and I'll just hold everything else in the processor, and I'll sort of fill that gap with no operations until the branch instruction gets to my execute phase, and I know for sure which instruction is being executed, and then I can proceed correctly. The logic here is a little bit different than the logic for the data hazard, and the reason is because in the data hazard detection, whatever is the follow-on instruction is going to execute. I'm going to execute this store register instruction, so I can use this logic here to sort of let that hold itself in this read register phase until the data hazard resolves itself. The sort of logic here for the branch unit in dealing with the control hazards is a little different, and the reason is because as soon as I detect this branch instruction, the add instruction is basically already in the program counter, but I don't know necessarily if that's the instruction that I want to execute next or not. So I have to sort of catch this branch instruction a little earlier and treat it a little differently, so that if it gets to this execute phase and I realize I am taking my branch, I don't accidentally have the next instruction somewhere in my pipeline. I can go immediately to the load instruction. All right, so not the most elegant, right? Just to sort of delay, just like our data hazards, this is going to reduce the performance improvements we see from our pipeline, but it's simple and it'll work. Strategy number 1.5, this is a slight variation on the same one, is to assume that the branch is not taken, meaning if I see this branch, I'll just assume that my next instruction is going to be the add after this, and I'm not taking it. But if I do take my branch, then I insert a bunch of no operations in my pipeline to start over correctly. So the logic for that is right here. My branch unit is basically, when it sees a branch, it's just going to let it proceed through the pipeline until it gets to this execute phase. So you can see here from my code snippet, when the branch is in the execute phase, the rest of this pipeline has been filled with the instructions that follow it, the two adds, and then the program counter is about to get the store instruction next. And we just sort of let that happen. And if the branch is not taken, hey, then nothing changes. My pipeline's full, and I can kind of keep executing exactly the way I had anticipated. However, if I do take a branch, then I do what's called a pipeline flush. So if I insert no ops in basically the entire pipeline, then I flush the whole pipeline, and I start my program counter back over at what should be the correct instruction. In this case, the branch target, if it is taken, was the load instruction. So up here, you can kind of see the basic logic for this, that if in my execute phase, the opcode is one of these two instructions, jump or JSR, right, which is basically a branch which is always taken. Or if the opcode is branch and I am taking a branch, then flush the pipeline. Insert bubbles in all these stages, and there's logic back here that that's already in the LC3 that detects that the branch target is the next value that goes to the program counter. So the benefit to this is that I can marginally get back some of my performance gains. I think I meant to put it in this lesson, but I'm going to show you this here. This is an example of the number of clock cycles that I pay in a penalty for my control hazards. So when I'm implementing that first strategy where I just say, hey, if it's a branch of any kind, I'm going to insert no ops until it's resolved, then effectively these should be, for this pipeline, the one that we're looking at here, those would be 3, right? Because if my branch is here, I potentially have instructions in this stage, and this stage, which get flushed or no ops inserted here if there's a branch. So I pay a steep price every time I branch. There's a 3 or 4 cycle penalty for that branch, and I can marginally increase that in this little corner here for my branch instructions if they are not taken by using this strategy 1.5, right? That's this strategy down here where I assume the branch is not taken. And if that's correct, then I don't pay any penalty because I've already have the correct instructions in my pipeline. But if it is taken, then I flush and redo, and I pay that 3 cycle penalty or that 4 cycle penalty in order to refill my pipeline with instructions after I take that branch. So again, just like data hazards, I have to deal with this because otherwise I will not execute this program correctly on my pipeline LC3. But I pay a price. So whereas theoretically a 5-stage LC3 pipeline should have a 5 times performance improvement over the normal LC3, I sort of eat away into that, that 5 times improvement when I add a whole bunch of jump instructions into my program. So and sort of just like data hazards, and how much it affects the performance depends on which strategy I'm using and how many of my instructions are branches. If I have a lot of branches in my program, well, then the performance is going to be a lot worse than if I have a very linear program with only 1 or 2 branches. All right, folks, that's all about control hazards. I'll see you next time.